Hello, I have 1:30 local time on my computer, so we're going to get started. For those of you who don't know me or recognize me, I'm Doug Cragen. I've been working here at Integrated Engineering Software for approximately 16 years, and I'm in charge of benchmark testing and customer support. As I mentioned, I recognize that the names of many people who are attending right now, and so I'm going to be splitting my comments a little bit. What I will be doing is to talk about some new features that are coming up in version 94, but I will be talking in a way that emphasizes kind of the flow of where we're going with new features in general with the program right now. If you're a user, you know version 94 isn't released yet. We're just in final implementation and testing, so this is a little bit of a sneak preview, plus, as I mentioned, talking a little bit about where we're at right now. And the particular focus of this webinar is going to be on the matter of efficiency. We're going to address that in many different ways. So why focus on efficient use of software? Why not just use the software and it is what it is? Well, software is a tool, and as the cartoon on the right shows here, picking the right tool and using it in the right way is important when you're doing a job, and simulation is no different than anything else for that. So when you're looking at software, beginning users often just look at the price. How expensive is the software? How much do you pay for whatever method there is for things like support, workshops, and updates, whether that's maintenance like our company provides, whether that's purchasing of new versions like others provide. How much do you pay for the software? But people who are more advanced, and especially, let's say, managers over groups, are much more aware of the cost of the software. That is, in order to operate the software, you're paying somebody to use the software. So you're very directly spending money according to how much time it takes them to do a job. Typically, it's going to be an engineer using our software, so if someone takes 2 months instead of 1 month to accomplish a particular job, you're paying 1 extra month of salary. Besides salary, there's what's called opportunity costs, and in academia, this is simply wanting to be the first to present results. In industry, this is typically time to market. So the longer your development time, the shorter the time you have selling. And sales being X amount per month, every month delayed releasing something is a month of lost sales. There's also the question of what else you could have accomplished with your engineering design staff in the time that you spent using the software. That's lost opportunity. There's also the cost of errors to consider. If you're not using something efficiently, you have a higher chance of producing unreliable results, and this is always relative to whatever your accuracy needs might be. And if you have unreliable results, what might that entail? Might it entail eventually product recalls, and so on? So those are all costs that are minimized by making the best use that you can of the tool in order to get the most accurate results in the least time possible. So that's why it's a focus of interest. So a large part of this presentation, the first few sections, will be focused on automation. Basically, whatever you can do that will automate the process of using the software will most likely result in more efficient use of it, less error-prone use and faster use in getting through a particular task. And the automation can do a number of things for you that will be covered in the upcoming slides. We'll break the automation into 3 parts here. Automation in the sense of things that you normally do, standard outputs for a project that you're on. What are you always going to be looking for, and how can you simply get those every time you do something? Our long-standing method of parametrics and our relatively newer method of scripting are two ways of automating in a much broader sense. And as I discuss those, I'll be coming back to the predefined, because that kind of is a basis for all kinds of things that you can be doing right now. So we'll begin with the defined outputs. For many years, Integrated has simply used a pull-down menu where after you solve a model, you go down and you say, I want to know the force, the torque, the power loss, the energy, and so on. Or you can open up a dialog where you could ask it for plots to be created. And whenever you ran a new solution, you would have to reproduce all the same steps, even for the same plot as you made the last time, even for the same preferred outputs as you did the last time. And if it involved a lot of selection, like picking parts to get a force, you would have to reselect the parts, which brings up the possibility, besides the tedious and slowness of doing it, that you'll make a mistake and at different times and different solutions miss some of the parts that you intended to include. So the process has been recognized as prone to errors. So a couple of versions ago, we added an additional interface. We didn't remove that interface, but we added a new one that allows you to predefine outputs and manage them so that you retain these outputs and you retain the automation of the outputs for however long you're working with the given project file. And every time you solve, you're going to rerun the same outputs, and you'll keep a history of them that you can review. And that holds for plots as well as for, as I say, things like force and field and so on. What we've concluded once we got going down this road was that our older interface is better for casual queries. That is, I have a result, I look at something, I say, no, I don't want to plot quite there, I want to plot over here. Or I don't want the force on those parts, I want to try it on these parts. It's good for casual work, but our new interface is better for systematic work. That is, once you know what you want, you predefine it, and then you're guaranteed that you've just got it. As soon as you've solved, you've got all your standard outputs sitting there. So one of the features of version 9.4 is that we're bringing these two together and ultimately working towards a unified interface. But for now, we've introduced the ability to do the casual plotting, and whenever you like a plot and decide you want to make it permanent, you can add it into the output system. So this is a transitional step in where we're eventually going. To provide an example of using this, I decided to make up a simple benchmark test case. This is something that I typically do and recommend to people at the start of any new project. When you're doing something different enough from what you've done before that you're no longer sure about the optimal way to set up the solver, then you should run a process of convincing yourself of what is the best way. So typically define a test case, decide on what output you're going to use as a measure of solution quality, and as far as possible, do those outputs for a particular case where you have a good estimate of the correct result. Perhaps you have theory, perhaps you have a measurement, but if possible, something where you already have a good idea so that you can verify the settings against that. So My chosen case is simply a rectangular bar magnet with a hole running through it as shown in the diagram. And depending on what you're planning to do with this, if you're embarking on a project where you're making magnets with holes and you want to reconvince yourself what is the best way to set up the solver, that's what we'll be looking at. There's three zones that I consider. One is just generally close to the magnet. Generally close to the magnet is pretty easy in all cases, but there's two challenging zones. One is right around the hole, you have an odd flux pattern because the flux is going upwards in general at the top of the magnet, but some of the flux returns through the hole, and that means that you've got an inflection point or a saddle point in the middle where the field is zero. Because the mass in this whole region basically involves cancellation of upwards and downwards contributions of the flux, the numerics are very tricky. And if this is a region of interest, then you've got to recognize that as a challenge, and that potentially, depending what questions you want, like you want to know where the zero is or what the field is in some point in space close to the zero, then depending on your solver, you may have to go through some extra work. The other problem zone is simply far away. If you're very far away relative to the size of the magnet, again, depending on your solver, that may introduce some challenges. So what we do is we say, this is our test case, and I chose to use ideal magnet characteristics. That is, the coercivity equals the remnants. And because of that, we can use analytic formulas to predict exactly what the answer should be at any of these points for comparison. And I simply picked 3 points, one right in the problem zone, one just generally close to the magnet, and one a distance 30 times the magnet size away. So that is going to potentially challenge the solvers in different ways. So, as I mentioned, the whole idea of the defining outputs is that every time you solve, we simply accumulate results. So in this case, I'm not asking for plots. I'm simply asking for 3 field at point values. And as mentioned in the middle bullet here, is I accumulate these by solving with the defaults and then using a feature we have where we just say, give me one step of refinement. I simply take our default settings and refine 4 times over. And you see the answer is extremely stable. The reason for that is that our default solver for this kind of problem is a boundary element solver, which does this kind of model extremely accurately. So I note in the middle bullet what the theoretical correct answers are, and you can see that the numbers are very, very close to those, even by default. If they're not good enough, I can simply carry on, of course, but I can also start doing some other things. So given that the answer is settled down, what I did was I worked with a solver setting called accuracy/speed, and existing users who aren't familiar with this and want to know can talk to me about it sometime. But what it basically does is it affects the accuracy of the computations at the expense of speed. So when you hit a limit where more and more elements isn't good enough, it's basically saying that the way we perform the numerics isn't accurate enough for your needs. So if you need extremely high precision and the elements refining hasn't done it for you, we can increase this number. And as noted here, the numbers now become accurate to all 8 decimal places shown once we increase that number. So again, this is a model which my guess would have been is best for boundary elements, and these results confirm it. and depending on your needs, it may have confirmed that just to set up the model and solve it is good enough, because that was far better than 1% accuracy. But if you do have higher accuracy needs, it helps you identify how much refinement and what type of features you want to use. And again, depending on the problem, we have many, many more settings than these that can be invoked. We also have a finite element solver, which is not our default for this kind of problem, and the reasons why show up in the table. It's not bad for what I called the easy point, the typical nearby point, but it's really not very good for the point near the zero. If I wanted good results for the point near the zero, I would need to take specific control over the elements there, so a lot more manual intervention would be needed. And it doesn't whatsoever give the far away result. The reason is that the airbox created, which the finite element method requires, is by default not that big. It would be wasted computation for that to be the default. So in order to get that last set of numbers in the red box to not be zero, I would need to make an airbox much bigger than 30 times my magnet size. And if you're familiar with finite elements, you'll recognize that that starts introducing a whole new set of problems. So that's why we default to boundary elements, but you can always go back and forth. And you see the utility of the output manager, even just for something as simple as maintaining a data table as shown here, is readily obvious. Rather than manually asking for the same numbers over and over and over every time I want to test something, I just accumulate a table, and I can use that table to create graphs and so on. So for this particular type of study, just a piece of advice, what you really want to do is to compare solver time. You don't want to just look at settings, because for all you know, my best case took a lot longer than my poorer case. So it's really solver time you want to be focusing on. I should also mention, I guess, solver time plus interaction time. And really, from the cost point of view, if a project is going to take the computer a week, for example, that's kind of a fixed amount of opportunity time for your release schedule, but engineering time is another thing. The computer taking a week is one thing, but the user spending 5 minutes, an hour, a day, or all that week is a whole other cost for you to consider. Parametrics are a way that we have of automating when your model is defined and you simply want to run variations on the model. And the new thing for us with parametrics, existing users will recognize we've been able to set up this kind of systematic study for many, many years, is that this region, where I've defined what I want to get out of all the variations that are going to run on this model, there's a good argument for doing this part of it with the define outputs instead of defining it in the parametric itself. And the reason for that is that very often out of parametrics, what people are looking for is videos like you see here. I'm moving the hole through the block and I'm changing the height of the block with my parametric, and I generate a video showing the result in the sense of what do the electric flux lines look like. I can also, from the field at point measurement that I took, make plots as shown on the right. But these videos, the problem with our old parametric is if you ran it, it would simply take a screenshot at every point while it's running and post those screenshots together into a video. So if you decided you wanted to change the angle of orientation, the coloring, the zoom level, anything about the video, you would need to reset your view and rerun the whole parametric. With the outputs, if you define your output, then run the parametric, you've got all of those results sitting there as defined plots. You can use the output manager then to create animations of any of those descriptions from the set of results. So the new defined outputs gives you much more flexibility for creating video animations from parametrics. But the strength of the parametrics is that it's very easy to configure. You saw the dialogue on the previous slide. It's very easy to configure just loops of take this, move it from here to here, change materials, and so on. The parametrics do require a user who knows the software, and it requires some time to reset up in every single model that you want to use it on, even if the models are similar. So there are some downsides to the parametric, and it's fundamentally limited because you can't do arbitrary things. You're just making basic variations on something that already exists. So a couple of versions ago, we introduced scripting, and we have been focused on greatly expanding the capability and the samples for scripting in the last few versions, because the scripts are what enable you to, with more upfront effort, do virtually anything. There's two general ways that you might expect to see scripting. One of them will be that we make up our own scripting language and put it inside our software. So it's all internal and self-contained. That makes the software look powerful, but it's got some drawbacks, and it really doesn't offer you anything. What we've opted for instead is to enable external scripting. So you can take an environment you already know, that you're already comfortable in, like writing macros from Excel or MATLAB or Simulink, or you can even custom create your own program. You can use Visual Studio to create a program. And from these other environments that you already know, you can reach into our software and take control. And the more control capabilities we give, the broader the things you can do are. So I'll present a few examples of that. So the big strength for an organization is this, that you can use a few expert users along with people who know how to do some coding in order to generate very powerful, very broadly useful utilities within the organization. And these can even be used by people with no knowledge of the software itself, who simply know what it is that you're doing in general. And here's my first example to kind of illustrate that. This is a device called a Haulback Wiggler, which consists of two magnetic Haulback arrays, one above the other, configured such that the maximum field is in the gap between for both of them. So if you were a group that kept designing and redesigning Haulback Wigglers, rather than creating them manually every time, the description is simple enough that you could simply create a tool like is shown here, where the parameters defining the Wiggler are editable. You simply hit the run button, and the program, start to finish, it does everything for you. You can appreciate that anybody who knew what the output you're looking for should look like, what they're looking for in that output, can now run this. They don't need to know anything about our software. So internally, it looks at something like this. We've indicated the Excel macro code that's being run when you hit the run button, and the red part is simply our functions. So it's Visual Basic code that's used for writing macros within Excel. and the red is simply where you're invoking 3 things from our software, and only 3 things need to be invoked to get the results. Set it to static, run the solver, and then in a loop go through and get the field at points, and those are written back into the spreadsheet and a plot is created. Further up to macro, there's other commands invoked to actually create the geometry. But at the end, after running it, you get a result like this, where the defined output is simply that we're going to produce the magnetic field along a particular line of interest. So as mentioned, the user doesn't need to have advanced knowledge. They just need to know what they're looking for. Change the parameters, run the script. So you can expand greatly the usefulness of the software by having expert users create tools such as this. Another example, this time electric, is an example of going a step further, saying rather than just pumping out into macro, we'll write a whole little desktop application that we can make use of. And in this case, it's an insulator design tool, insulators like you see at the top of power poles and so on, defined by a number of parameters, but again, regular enough that you can define it with a reasonably short list. Materials, widths, separations, angles, and so on. And then over to the right, define what outputs it is that you want. So every time that you change the outputs and run it, you see the graph being updated, you see a data table being updated, and if it's a user who knows what they're looking for, you can ask the program to automatically create results such as the electric flux lines being shown on the right. But writing utilities like this, again, gives you a very self-contained desktop application that expert users can create, that anybody can make use of for doing more systematic run-of-the-mill work. But projects don't have to be start to finish to be scriptable. A lot of scripts are simply used for the purpose of performing some standard operation. So mechanical coupling is a good example of this. Here we've got a very simple model where we've got a rod of steel inside of a current-carrying solenoid. So as we release the rod, it's going to pull towards the middle, and depending on friction and so on, it's going to overshoot and oscillate back and forth. So you can see that generically just by looking at field plots that you can't make any mechanical predictions. To make mechanical predictions, you're going to have to invoke some kind of mechanical solver. So we can do that a number of ways. For many years, our parametrics would let you output results that you could send into some other program. And the program that we represent in North America is this one called CASBOC. It's a power electronics and system simulator. There's many of them out there, but for what it's worth, if you like to work with us, that's the one that we represent and can most directly help you with. For the purpose of demonstrating scripting interaction, we can use Simulink as a very powerful and popular system simulator, and Simulink operates from within MATLAB. One of the things that you can do from Simulink is invoke MATLAB functions, and MATLAB functions can invoke our software. So what can we do to set up, independent of what Simulink toolboxes you may have, and there's toolboxes that could do this more directly, but independent of that, what can we do just from the basic Simulink? Well, remember that acceleration is the second derivative of the position with respect to time. So Simulink is going to work with position and time. If I feed the position into a MATLAB function that invokes our magnetic solver and it runs a simulation to give you the force, convert that into an acceleration and feed that back out again, then if I do two integrations on the acceleration, I've advanced at my position. So I put a couple of probes on this so that I can output the position and the acceleration, and Simulink is simply going to time step to go around and around this loop. And after it's done, so we get the curve that you see here. So the position and the acceleration are varying as you should expect. Again, similar to a mechanical spring. Inside, the code is again similar looking. What we invoke within the MATLAB function is extremely simple. All it does is it says, take the position, displace the block to that position, run the solver, get the force, put the block back where it was, and then return the force divided by the mass so that you're giving the acceleration back to Simulink. And here is the result, and again, playing off of the defined outputs. Before I ran this with Simulink, I defined that I want to get a magnetic field line plot. And that means that every time magneto solved, it updated the field line plot. So for constant time steps, which is the way that I configured Simulink to run, I have the position of the rod being updated and the flux lines updated with it. So all these different automation methods are not independent of each other. One can couple them together like this so that when I'm finished running my simulation, I get an interesting plot like this. This is all the details of the magneto model, and the thing to note about my Simulink example here, if I go back one slide, is that it's simply displacing something named block. So within our software, you can name parts of your model. So if I give a name of block to anything in one of our programs, I can run this script on it. I can use it on electric models to get electric forces. I can use it on magnetic models. All I need to do is to edit these numbers for volume density and so on if I want to. And I can run this exact script. I don't need to redo it for different models. So this is reusable. This is saying that if this kind of mechanical simulation is useful to you, you can run it on any model, and another model might produce whole other animations for you. The script isn't in charge of that. One more example. A lot of very large geometry that gets made is very regular, but some of it is kind of quasi-regular, like the pancake coil shown here. So the pancake coil, every section is a little longer than the last section. So there is no easy copy-paste repeat operation that's going to generate this whole coil. But it is a regular enough process that you can define it by a few parameters and write a script to generate it. So this is one of our newer sample scripts that we ship that lets you generate a pancake coil. But we have users who've done many other generically similar large things like this, and much larger than what's shown here. I made a geometry large that you can recognize would be tedious to make manually, but not exceedingly large. We've had customers make plates with thousands of irregularly spaced holes in them, for example, something that will be extremely tedious and again prone to error to do manually. So before I move on to that, let me just think. Yeah, let's just move on. So that's the automation section. Some other things that we're doing to try to reduce tedious aspects of the program. This is one long-standing issue for me, is that when you compare plots like arrow plots and contour plots with graphs that are created, an obvious thing is that arrow plots, I immediately know what the information is. When I produce a graph, I don't know. I see graphs, I don't know where in the model any of that information refers to. And we've been meaning to tackle this for a long time, but existing users will know that we used to have a separate pop-up program that we did the graphing in. So a big feature for version 9.3 was to simply bring the graphing into the main program. And the reason for that was that what we're now doing in version 9.4, we can now directly make graphs and the model interactive with each other. So as an example, when I click on a graph, or even when I just mouse over a graph line, it highlights in the geometry. So I can immediately see now this line, where is it in the geometry? So for a graph that I've just created, of course I already know that, but for a model I made some time ago or that I got from a coworker or a customer, I don't know any of that. I've got to try to figure it out. Again, a time-consuming part of using the program. So the highlight, move a dot along so I can move my cursor over peaks and valleys and see exactly where those correspond to in the geometry. So besides that, we also created a new type of contour plot in this version, and we made them interactive with the graph. So if I make a 1D contour, then I can present it either as a graph on the right or as a 1D contour or as both. So for the two graphs that I created there, I can turn on 1D contours, and now I see colored right in the geometry the same information as appears on the graph, and I can still do my trace thing to identify particular points, but I can very directly see in the model window the information I get from the graph. So again, identify peaks, valleys, and all that kind of thing very quickly, even for something that I'm not immediately familiar with. In our electric program, one of the long-standing issues for some customers has been isolated sources. If we look in general to motivate this a little bit, if I have a battery sitting in empty space, you know that one terminal is not at 0 volts relative to anything other than the other terminal. So I could say this terminal is 0 volts, the other terminal is 9, or I could say this terminal is 1,000,000 volts and the other terminal is 1,000,009. There's only relative meaning. All the charge from one goes on to the other if there's no connection to other objects. So this is what we've called balanced charge in our software, and it corresponds to voltages that you don't know relative to any real-world grounds or other potentials. It's limited in many ways. One of them is that you can't have two. If I had two batteries sitting there, I wouldn't know what potential to set for them relative to each other. But for a lot of cases, it's the right answer. A lot of equipment is run off of isolated sources. So we retain this, but we've wanted to make it more powerful in a number of ways. And one is simply this: we want to be able to have both an isolated source and a ground in the same model. So that's what you see here conceptually. I know that my zero terminal is not actually zero. I'm going to call my ground sheet zero. I know that my minus terminal is something. And then my 9-volt terminal is the same something plus 9. So we introduced a voltage difference source to accommodate this. And what it lets you do is to set one object as a reference and another object as a voltage relative to that reference. And now we can actually generate this. We can put our battery close to a ground source, and the program will solve for you what the voltage is on the battery. And you'll see it's not 0 and 9. It's a little bit above 0 and a little bit above 9 by the same amount. And to show this most clearly, I put on a log scale here. Otherwise, this is close enough to 0. It would just be looking blue at the bottom. We can also do this on multiple sources now. So previously with one source, you could have done this iteratively. You could have run a parametric, for example, where you kept the 9-volt difference but kept increasing them. But that was tedious to do. And if you had 2 batteries, now you would have had to do 2 loops and so on. It grows increasingly more difficult. But with the isolated sources, I can say here's one pair of voltage differences and then here's another pair of voltage differences. So we can see how we're kind of stepping up a little bit even without attaching the batteries together. This battery is going to be at a voltage a little bit above ground potential, and this battery is going to be at a voltage swayed a little higher still because it's close to the 9-volt terminal of the first battery. So if we move them even closer again, then we push our voltages up higher. On the previous slide, it pushed up to about 10 volts. Move them closer, we push it up to 12. And of course, if we push it in to contact, then we'll be getting more like 18 volts up at the top. So last feature to note before going to questions. This is a 9.3 feature, but it's new enough that it's worth mentioning to any magnetic users out there. And it is something that is new and therefore under continual improvement right now. Previously, our coils and windings were only available in 2D. So up on the menu, you see volume current here. If you know your current, you could assign that in either 2D or 3D, and you still can, of course. But in 2D, we had a specific feature that lets you configure coils, configure resistance, turns. You could apply voltages or currents to them and configure those into windings. But as you can see, it was just a set of flyout menus. Very obscure to use, very tedious to use. You would just keep going back to the menu over and over and over, and again, error prone. You click and you maybe misclick on the wrong thing. So we wanted to get that into 3D, and we wanted to make the whole process easier. So in version 9.3, we replaced all of that in 2D and 3D, introduced it with this dialog, which has 3 tabs. One where you configure types of coils, one where you configure coils, one where you configure windings. So the coil editor lets you define a type of coil, which consists of how many turns there are and what the resistance is. The coil properties let you create coils out of those. So out of the same coil type, you can apply to multiple coils. The coil can be defined by saying which volumes you want to include in the coil. And finally, you take your coils and you configure them with each other and with sources and loads in order to define a winding. So the entire process is much more transparent here, much more obvious to the user with more visual feedback than the previous method. So this is a matter of a tool that we've greatly improved and which warrants some consideration. One heads up that I'll give to users who appreciate the benefits that I mentioned earlier of the boundary elements. In 2 dimensions, this method works for either finite elements or boundary elements. In our 3D, it presently only does work with the finite elements. So if you prefer working with the boundary elements, this is not an option right now, but of course that is something that is on our list of improvements to make to this. So summing up the webinar, we've presented some of the newer features in Integrated, focusing on version 9.4, but trying to put some context on that with an emphasis on items that improve the efficiency of using the software. We've provided a few examples to illustrate automation of the simulation through defining outputs, parametrics, and scripting. And a quick comparison of the two, if you're going to do something very quickly on one model that's simple variations of the existing design, do it parametrically. That's very fast and easy. But if you want a generic tool that you can apply to multiple models with much broader use, and you're willing to spend the upfront effort that's required in order to generate a script for that, then scripting is your choice. It'll create something much more versatile and much more useful in the end. So that's the end of the formal part of the presentation.